Welcome everyone to the Flow seminar. Flow stands for Federated Learning One World Seminar. So it's a pleasure to have Qinbin Li today as a speaker. He did a PhD in Singapore and now moved as a postdoc to Berkeley last year. And today he will talk about FED3, Federated Learning Systems for Trees. So please feel free to ask questions during the talk or at the end of the talk. And as the audience is quite small today, so we can accommodate all your questions or concerns. Okay, so Qinbin Li, please go ahead.
Yeah, thanks for your introduction. Thanks for having me in the seminar. So today I'm going to introduce FED3. So we are all familiar with federated learning. So multiple clients collaborating in training a machine learning model without changing the local data. It has been a very hot research area. The number of papers about federated learning increased rapidly. If you ask ChatGPT to protect the privacy of trained data, so one technique mentioned is federated learning. And it has been also included in the research plan of the White House. So it's a very hot research area, and we know that Federated averaging is the fundamental method. So in this approach, the server sends the global model to the clients. The clients update the model using this local data and send back the models, and then the server average the models. So this is a very simple but powerful method for federated learning. Basically, it's based on distributed stochastic gradient descent. Basically, instead of transferring gradient for each batch, here we locally update the models multiple rounds and transfer the models. So thanks to federated averaging, nowadays we have many federated learning systems. Google has TensorFlow, Federated, OpenMind has PySafe, and there are also other systems, Fate, Flower. So many systems, thanks to these systems, they play an important role in the deployment of federated learning. But today, if you look at the federated learning system, yeah, they are popular. If you look at the stock history, for example, PySafe, I think it's the repo with the highest number of stars in GitHub. So now it has reached over 8,000 stars. So it's becoming hot. So PySafe is popular, but it's for deep learning. Okay, so if you look at this federated learning system, actually they're usually for deep learning. If we look at today, I'm going to take you to look at another model, decision tree. So here I show you the star of another repo, XGBoost. So XGBoost is a gradient boosting decision tree system. So you can see that actually it's much more popular than PySafe. It has reached over 20,000 stars. So we can see that although nowadays most people, if you go to an AI seminar, actually, I think over 90% of the people, they are talking about large language model. But besides deep learning models, actually trees is also widely used and also popular in the industry. So today, we're going to look at trees, this kind of model. So if you compare deep learning with trees, so for deep learning is powerful and powerful. Okay, we have large language model. So now most people, they are using a large language model. But if you look at trees, so compared with deep learning, tree also has some benefits. For example, explainability. It's very easy for you to understand a tree. How does the tree make a prediction? You just look at the speed rules. You can explain its prediction. But if you want to explain the prediction of a large language model, it's very challenging. And also efficiency. To train a tree, you just need seconds to train a single tree in your Mac. But to train a large language model, usually in academia, you don't have the power to do that. In industry, they may have hundreds of or even thousands of machines to train a model using months. Okay, so for the efficiency, tree is much more efficient than deep learning. And also, we know deep learning is powerful, but for tabular data, actually, many studies have shown that decision tree is better than neural networks for tabular data. But tabular data actually is still the widely existing form in industry. We have the relational database, we have many database which stores the tabular data. Okay, so tree has many benefits compared with neural networks. So let's go back, let's take a look at trees today. So here I show you what is a tree. For example, the gradient position decision tree. So here, gradient position decision tree is basically multiple trees because a single tree is too weak. So we train multiple trees for the prediction. So here we train 2 trees. Let's say we are predicting whether a person will attend new reefs or not. Okay, so we train the first tree. We split by the age smaller than 90 or not. Is the age is smaller than 90, and we determine by whether the paper is accepted to new reefs or not. Okay, if it's accepted, we have a prediction value. If it's not accepted, we have another prediction value. And then after we train the first tree, we train another tree. Let's say whether this person is a machine learning researcher or not. Okay, we have another prediction value. And we train many trees. Here, I just show you an example of 2 trees. And our final prediction value is the sum of prediction value of each tree. For example, is 0.664 plus 0.234, which is 898. Okay, so for a tree, we have 2 kinds of nodes, split nodes and leaf nodes. The leaf node is the leaf value, the split node is the split condition. And for the gradient positioning tree, we train multiple trees with sum the prediction values. So for this kind of model, it has many applications, for example, used in finance and used in healthcare. And also maybe this is where you know it in Kaggle competitions. It has won many awards in Kaggle competitions. Okay. So tree is useful, and XGBoost is this library is powerful, and XGBoost actually they have distributed version. They support a distributed computing setting. But in their setting, what they assume let's say they have a system, they has the global data. For example, they use Spark array. They use this system to allocate the data and the task to different nodes. Basically, they want to utilize distributed resources to accelerate the training procedure. Okay, so they allocate the data, they allocate the task. So this is not the Federated setting. In Federated setting, what we have is the data naturally distributed in different nodes. And we may have a server to aggregate the results. So this is what we want to do the federated trees. Okay, so how do we implement a federated tree system? So first, let's look at the centralized gradient position decision tree. How do we train the tree in the centralized setting mathematically? So this is our loss function. So the loss function has, first we have the loss, compare the prediction value yi tau and the label yi. So let's say if we are doing the regression, we have the square loss. And then we have another term, which is the regularization term, omega f. F is our tree function. We have multiple tree, so we have multiple f. The regularization term, so we are to reduce the complexity of the tree. So basically it's depends on some parameters, gamma and lambda. And the T is the number of leaves, and the W is the leaf value. Okay, so this is our objective function. So how do we optimize it? So we are doing boosting. We are training a new tree at each round. So at round T, we train a new tree ft x. Let's say we have a new tree ft. So for the previous t-1 trees, we have the prediction value yi t-1. And now we have a new tree ft. So we sum the prediction value. So this is our updated prediction value. So this is our loss function at round t. So how to solve this equation? We do the second order optimization. We have the first order gradient gi, which is the gradient of the loss function with respect to the prediction value. and h, which is the second order gradient of the loss function, with respect to the prediction value. So we do the second order approximation to optimize this loss function. And then we remove the constant term. So we want to optimize the remaining part. So what we do is that let's just expand it. We replace the tree function with the leaf value. The leaf value is w, and we return the regularization term with the number of leaves and the leaf value. So here basically, if you think the leaf value w as the variable is a quadratic equation, we can easily solve this quadratic equation. So the optimal w, the optimal leaf value, is this formula. Basically, is sum of the first order gradients of the current node divided by the sum of the second order gradients plus a parameter lambda. And also, this is the leaf value, but how do we determine how to select the the speed value? How do we determine is h smaller than 90 or is something else? So after split, we have the left nodes and the right nodes. So we can compute the gain of the current split by using the let's say after split we can have the loss function. We have the loss, and before split for the current node we have the loss, and we use the loss after split minus the loss before split. We can get a gain of this split. Okay, so this is our gain. After, if we subtracting these two loss, we can get the gain of a split. So we can try different split. We can compute the gain of each split, and we can select a split value with the maximum gain. So it sounds that okay, we know how to train a tree now. So for the split nodes, we just try every possible speed value and we find one speed value with the maximum gain. But it seems that it's too costly. You have to try all the possible speed values. You have to try many, maybe thousands or millions of speed values. Okay, so what we usually do is to do the histogram-based learning. So instead of trying many possible speed values, we propose some cut points. For example, for the age feature, we don't try every possible value. What we do is that we just propose, let's say 30 and 60 as the possible speed value. Just try these two. Try to split by age smaller than 30 or not, age smaller than 60 or not. We just try these two speed points as our cut points, and we have the gradients, right? The first order gradient and the second order gradients. And based on the cut points and the gradients, if you look back at the formula, you see that what we need is actually sum of gradients of a node. You see, for the leaf value, we need is sum of gradients, and to compute again, what we need is also, sum of the gradients of the left node and the right nodes. So here we can have the histogram, which is the sum of the gradients. For each cut point, we split the instance to left side and right side. And for each side, we can compute the sum of gradients, which is our histogram. Okay. So based on the histogram, we can compute the gain, it's also sum of gradients. Basically, just using the histogram, we can compute the gain of the speed to get the one with the maximum gain, and also we can compute the optimal leaf value based on the histogram. So if you look at the flow, we can see that the histogram is the most important part. As long as we have the histogram, we can get what is the best speed value, what is the best leaf value. We can get the tree. So let's come to the Federated setting. So in the Federated setting, we have to aggregate the knowledge of different clients, but we cannot use Federated averaging. Federated averaging is based on gradient descent, but you see for the tree model, the tree parameter is non-differentiable. We cannot use the gradient descent to directly optimize the tree parameters. So we cannot use gradient descent, we cannot aggregate the models, we cannot directly average the tree models. So what we do is we can aggregate the histograms. Let's say, how do we do the histogram based variety learning. So first, for example, in the vertical variety learning setting, we have a bank, we have an e-commerce company. So they have different features of the same user. So they can do variety learning to improve the model on the task. So the bank can compute the histogram for its features, let's say feature 1 and feature 2. The e-commerce company can compute the features, can compute the histogram for its feature, let's say the another feature D. So to get the histogram of the global data, how do we aggregate the local histogram? Actually, it's very easy. Let's just do the concatenation. Because the features, each feature, they are independent of each other. So the banks has the histogram for some features, the e-commerce company has the histogram for other features. So to get the global histogram, we just need to merge them to concatenate them. This local histogram, we can get the global one. And so this is the vertical variety learning setting. They have different features. But for the popular setting, for the horizontal setting, let's say we have multiple banks. The banks has different users. For example, the origin part is held by a bank. The blue part is held by another bank. How do we merge the histogram? So we can just do the sum. We just sum the histogram. For example, for these cut points, for this part, we just need to sum the histogram of the orange part and the blue part. We can get the global histogram. So by using concatenation and the summation, we can already, aggregate the knowledge of different clients in variety setting. So this is our framework. Instead of training data or model, what we transfer is histogram for training. So there are multiple rounds. Each round we have multiple steps. The first step, we do some initialization to show the common parameters, some help parameters, and then for the clients, they have the data, they compute the local histogram for its local data, and then they show the histogram to the server. The server aggregates the local histogram to the global histogram, and by using the global histogram, it can update a node. Is a spin node or is a leaf node. You have the formula, you can compute it. So after you get the node, you send back the node, the tree node. So here is the node is the tree node. You send back the tree node to the different clients. And then the clients can update the model. And then for the next round, you update the histogram and do it again. Okay. So this is the framework. So I think it should be easy to understand. So what we do is to aggregate a histogram. So for variety learning system, one thing we have to consider is the privacy. Because when people want to deploy variety learning, why they deploy variety learning, one thing matter is the privacy. So for privacy, one thing is the label privacy. We want to compute the gradients, right? We want to compute the histogram. The histogram is based on the gradients. But how do we compute the gradients? The gradient is computed based on the prediction value and the label. So we need label to get the gradients. But in vertical variety learning setting, some clients, they don't have the label. They cannot compute the gradients. How do we solve it? One thing is that we share the label. Everyone has the label. They can compute the gradient, but sometimes you cannot do that. You have to protect the privacy of the label. So what we do here is that we apply additively homomorphic encryption. So let's say the bank has the label, the e-commerce company, they don't have the label, they cannot compute the gradients. So the bank can compute the gradients. After computing the gradients, it can use additively homomorphic encryption to encrypt the gradients. It sends the encrypted gradients to the e-commerce company. Okay, the e-commerce company has the encrypted one, cannot decrypt. It only has the public key. The public key can use to do the computation, to do the addition computation on the encrypted gradients. Because for the histogram, what we need is only the addition operation. Okay, so we can use the addition operation to compute the encrypted histogram locally. Okay, so here we only need the we don't need the label. We only need someone with the label. You show the encrypted gradient to me, and I can compute the encrypted histogram. I can show back the encrypted histogram. You can decrypt it. So during the whole process, we can protect the label privacy through additively homomorphic encryption. And one benefit is that, compared with other cryptographic methods such as the fully homomorphic encryption or other secure secure multi-party computation method, the additively homomorphic encryption has a low overhead because it only has to support the addition operation. Okay. So besides the label privacy, we share histogram here, but histogram may also leak something about your data because histogram is sum of gradients. Gradients reflect something about the label. So to further enhance the privacy, how do we protect the histogram? So one thing we can apply here is secure aggregation. For each pair of clients, we inject symmetric noise to the histogram. And because in the horizontal fabrication case, what we did is to sum the histogram. So in this, during this case, so the noise comes out with each other. We can get the global histogram accurate, the accurate global histogram. Okay. So this is secure aggregation. Another way we also support is differential privacy, because secure aggregation cannot prevent you from inference attack. You still have the global histogram. So differential privacy here, basically we inject some noise. Basically, differential privacy want to guarantee that when you change a single record, it doesn't affect the output much. Okay, so here we inject some noise to the histogram. We clip the gradients. We inject some noise. We can get a differential privacy guarantee. So this is for the privacy part. So besides the privacy part, another thing is the efficiency, because for a system we want it to be efficient because people have to deployment. We want it to be efficient to run in different devices. So one thing is how to speed up, how to reduce the computation time. So if you look at how do we turn a tree, so we have a node, we split the data into left side and right side, left side and right side. And for each node, we compute a histogram here. So here we have some parallelism technique. So between different features, because different features, when you compute the histogram, they are independent of each other. And between different nodes in the same level, they have different data. The data are split into different nodes. So it's also they are independent of each other. It's also a parallel procedure. So here we can do it in parallel to compute the histogram between different features, between different nodes. Okay. And another thing is communication. We share the histogram to the server. And actually, if you compare it with Federated averaging, in Federated averaging, we share models. So the size of histogram is much more smaller than model. The model you can, even for small model, you can have maybe hundreds of megabytes, or for large model, you can have billions of parameters. So the communication size of neural network is large, but here the communication size is quite small for each histogram. For example, because you propose some cut points, for example, you only try 100 cut points. For each cut point, what you have is just a single value for the sum of gradients. So usually for the histogram, you compute the histogram, you may cost less than 100 megabytes. Even sometimes it's even 1 megabyte. So the computation size is small, but But one thing is that the communication frequency is high, because you see that for each node, we have to communicate the histogram. So there are many histograms. So in Federated averaging, you update the model, and at each time you transfer the whole model back here. Each time we transform a histogram. So the communication frequency is high, and we find that the overhead of launching the communication protocol is even higher than you communicating, even higher than the communication itself. So we need to reduce the overhead of the launching the communication protocol. So what we do here is to do the batching. We have a queue locally, and each time you finish the computation of the histogram, you do not send it immediately. You store it to the queue, and until the queue is full, we send this whole histogram to the server, so that you don't have to launch the communication too many times. So this is to reduce communication size. And another technique for the computation is to utilize GPU, because although the training of tree is very fast, but if we apply additively homomorphic encryption, it's still, because it involves some encryption operations, it's still costly compared with you do not use the encryption methods. So what we do is that we utilize GPU. When you're doing the encryption operation, we use GPU to do that. Okay, so in this way, the CPU and GPU, they do it concurrently. The GPU do the complicated operations for some encryption operation, and the CPU do some normal operation to speed up the computation. Okay, so this is our optimization. So this is our architecture. We have the interface, command line interface. We also have the Python interface. You just need to specify some parameters, and we support, you do the simulation on a single machine, or you do the real deployment on multiple devices. And also for the frameworks, we support horizontal variety learning or vertical variety learning. And also for the privacy, we have the secure application to train the privacy on the homomorphic encryption to enhance the privacy guarantee. And for the tree, based on Boston, so we mainly support the gradient Boston decision tree. You can do the classification or the regression task. And to use our system, it is very easy to use. To install our system, just 2 lines, and you can write the parameter in a file, and you can launch it in different machines in a single command line, and you can get some results. Okay. So for the evaluation, we try to set it one simulation on a single machine, one is a distributed deployment, and we try some baselines, XGBoost, Fate, local training, Federated. So this method is, so XGBoost is the centralized training. We do not consider Federated setting. Let's just assume we have the whole data. We do XGBoost to measure the model accuracy. Fate is another system. It has many Federated learning algorithms, including trees. And the solo is that we just do local training without federation. And then the last approach that we do a tree level aggregation. So each party train a tree, and we aggregate these trees. Okay, it's a very simple aggregation method. And we do experiments on some tabular data set. Here for MNIST, we convert it to a tabular data, use the pixels. Okay, so first we compare the accuracy on this data set. If you compare our method, that tree, with centralized setting, you can find that our approach is lossless. Because we are doing a low-level aggregation. For each node, we are trying to aggregate the knowledge of all the clients. So our approach is lossless, even though compared with the centralized training, there is almost no accuracy loss. And then if you say, let's say, do secure application or home encryption, because they are free cryptographic methods that do not affect the accuracy. Okay. And then if we compare the so if you compare factory with a tree-level aggregation, you can find that the tree-level aggregation has some accuracy loss. Okay. If you compare the efficiency, let's say compare with Fate for the single machine setting and the distributed setting, our system is much more faster than their system. Okay, the speed up can be for the horizontal one in the single machine setting, speed up can be up to 66, and for the vertical it can be 25, and for the distributed setting, the speed up can be 80 times, and for the vertical can be 22. So our system is much more faster than Fate. And for Federated learning, what we usually do is non-ID data. Okay, so here, if we try non-ID data, is there any effect on the performance? No, there's almost no performance degradation, because still we are aggregating the histogram in each node. So our approach is lossless. If you try the label imbalance or feature imbalance, you can see that there is almost no accuracy loss. And we have some application study. For example, we do the batching. For the communication have the batching technique. If we have the batching or without the batching, so this is the first column is without batching, the second column is with the batching. You can find that for the communication time, we can have up to 5 times speed up with our batching technique. And also for the computation technique, for the parallelism, for the GPU speed up, you can see that with parallelism, we can reduce the computation time a lot. With our GPU acceleration, we can reduce the computation time further. Okay. And then for the scalability, here we just try up to 32 machines. We haven't tried a cross-device setting on the thousands or even millions of devices. That's our future work. So here, in these machines, we can find that our system can scale well. Okay, sorry, this should be the training time. Okay, and our system has some industry. Some companies, they have shown interest on our system. For example, the EM Group and AI Singapore, because sometimes they want to use it for energy prediction. And Amazon also, they have interest in using factory for anomaly detection. So in conclusion, our system is fast. We have 80 times speed up compared with the other system, and our system is effective. The accuracy is the same as you do the centralized training with all data. And it's also secure. We have some methods to further enhance the privacy. And you can scan our code here. So this is our work factory. And besides factory, I can briefly introduce some extension. So in factory, what we do is node level aggregation. You see, for each node, we aggregate the knowledge of each party. So this is the node level aggregation. And another method is to do in node level aggregation, the communication is frequent. Another way to improve the efficiency is that we do the tree level aggregation. Let's say the first client, they train a tree, they share it to the second client. The second client, based on the previous trees, it train another tree and share all the trees to the next client. Okay, so until we reach the trees we need. So this is a tree level solution. For this solution, is efficient, but it will reduce the accuracy, because here you just use the local data to train a single tree. And we have another word, how to improve the model performance in such a setting. Basically, we utilize some similarity. We use locality sensitive hashing to collect some similarity information. So during the local training, we use the similarity information together with the local data to train the tree to enhance the final model performance. So this is tree-level solution. And another trade-off is that between node-level solution and the tree-level solution, the tree is very flexible. What we can do is to do a layer-level solution. Let's say this tree has several layers. We ask one client to update the first few layers, and we ask other clients to update the next few layers. So one benefit is for this approach, this is our recent work. So we show that even though for hybrid data, let's say between some clients, their data are in the horizontal space setting. Between some clients, their data are in vertical setting. So basically, it's a hybrid data setting. So the layer level solution works well on this hybrid data setting. Okay, so basically these three level solutions show that tree is flexible in different trade-off. So trade-off between efficiency and the accuracy, we can have different solutions, low level, tree level, layer level. Okay. So for the future work, one thing is we can do cross-device variety tree learning. In the cross-device setting, we have to consider some sampling. And again, because in the cross-device setting for the mobile device, they have maybe very limited computing resource. So we have to consider the trade-off. And another thing I think, yeah, maybe that's most of us are interested in now is language model. Okay, so virtual learning plus language model, what happens? So language model or foundation models, they are powerful. So currently we have these powerful models. So one question is, do we need virtual learning? There are already many powerful models. We can just use these models. Why do we need virtual learning? So, but one problem is that if you look at these large language models, they are developed by the companies. Basically, one company develop one large language model because they have resource, they have data, they have resource. Okay, but can we utilize the distributed data resource? I mean, everyone can contribute. You can contribute to your mobile phone. You can contribute to your iWatch. You can contribute to your laptop. You can contribute your data and resource. So we can consider how to train the large language model in the distributed setting to break the monopoly by the companies. I think that's a very challenging direction, and I believe that some researchers and some industry they are doing this direction. And another thing is that federated training of large language models is challenging. Another thing we can consider is how do we tune it for private domains? Because we know that foundation models, they are powerful, but they don't have some domain-specific knowledge. If you ask the large language model, if you ask them to solve something related to healthcare, they may not be able to answer it. So they lack such domain-specific knowledge. But for this sensitive domain, we lack public data. So what we can do is to do a variety fine-tuning. We have the foundation model, we have several local data, we have the private data. How do we tune this model? Or how we can have some personalized model? For example, we can utilize trees. We can have the personalized trees in each site because the large language model is too large. So each party, they have the personalized tree combined with the large language model to do the tuning. Okay, I think that could be an interesting research direction. Okay, so that's all for my presentation today. So any question?
Okay, so first, thank you for your talk. And yes,
welcome.
okay, so I find it very good, research. If you also provide the code, with few lines, where we can try this out and test it. It's very, very
Thank
good.
you.
And also that you go a bit in different direction, or just not federated learning for let's say the standard deep learning models, but also try out a bit different, like these trees and so on. Very, very nice. Okay, so we have one question from the audience. So Pucha, you can just unmute and ask. Yeah.
Yeah, hi. Thank you so much for this amazing talk. Really nice work. I have one question regarding the metrics used for evaluation. You have used root mean square accuracy. So have you
Yes.
also checked other metrics? Say, for example, in real world scenario, when we are checking the finance data, it's say, for example, the credit risk data set and all, they are highly imbalanced. So in that case, what would be your suggestion? And even if we use it in finance, like, in healthcare, we see it's highly unbalanced. So I see the results are based on the data set which are quite balanced. So have you also checked the other metrics?
So you are saying that that is a good question. You are saying that the data distribution of different clients are very imbalanced, right? So we didn't try the the natural Federated data set. What we do is to do the simulation. We try the imbalance setting here. Basically, we partition the data to different parties and in an imbalanced way. So the label 90 is, let's say, the label distribution of different parties, they are different. The feature is that the feature distribution of different parties are different. So in such a setting, our method still, there is no accuracy loss because we aggregate a histogram from all parties in each node. So even though it's a non-ID data setting, what you aggregate the global histogram is still the same.
Okay. Thank you so much.
Yeah. Thank you.
Yeah, I've also maybe a question a bit in similar direction. So could you again explain how you've determined these cut points basically? So
yeah, that's a good.
Is this like automatic, or do we need an expert for this, or what is?
That's a good question. So for the cut points, so for example, in this example, so what usually what we do is to split the instance balancedly. For example, let's say we have instance these features. How do we determine the cut points? We evenly divide the instance into, let's say if we have 10 cut points, we divide it into 11 parts. We get this 10 cut points. We want to, basically our main goal is to ensure that the number of instances inside 2 cut points is equal, is a balanced way. So that's how do we determine the cut points. And here actually, also we have some mechanism for the cut points. For example, one thing is that the server proposes the cut points. Everyone share the same cut points. Another thing is that the clients propose the local cut points and we aggregate the cut points. So we have different mechanisms for it.
Yes. Okay, but in this figure that you showed, now you said, oh, you get the same result for centralized and for federated. So you use the same cut points for both methods, no? But
yes.
But it's not necessarily the case that if there is in the real world settings, no, we would have maybe difficulty to come up with the same set of cut points if no user.
Yeah, because we use the server to come up with the cut points here.
Okay, but you say that it's guaranteed that the server will find the same cut points even if the data is distributed.
Yeah, because so here the procedure is that, so first the parties will share some information to the server. Yeah. The server has the information. Let's say it know the feature range. Okay, the server will propose the cut points. So the feature range is fixed.
No, exactly.
No.
Okay. So the nodes share the range, and then you maybe equally split the range or something like this. So some
Yes,
okay,
yes.
Okay. Yeah. Okay, but then if there exactly, but if there, let's say there is the data is really split, that there is no overlap in the range and crazy situations like this, then maybe that you're a bit in trouble. But you say for typical situations, this might not.
Yeah. I think what you mentioned is is an interesting scenario. And what we can do is that we can let the clients propose the cut points locally. You have your local data, right? You propose the cut points locally and you share the cut points to the server. The server can aggregate the cut points and send back the cut points.
Yeah. Yeah, okay, thanks.
Yeah.
Just to to clarify a bit how this works. And then in terms of, I don't know, I'm not so familiar anymore with this literature on trees and so on. I mean, what kind of guarantees can you maybe prove there, or what kind of guarantees did people prove for, let's say, the centralized models? And do you think some of these can be transferred to the federated approach you propose, or is it more like evaluation by the numerical study?
You mean theoretical guarantee for?
Exactly. I mean, I'm not even aware. Do some theoretical guarantees exist in some way or the other for these three models? And could you think of some of these techniques that could maybe be used also to prove something for the federated case, or you have not thought in this direction
Oh,
properly?
you mean besides trees, other models?
No, for the trees, no. So.
Oh, yes. So sorry, I don't quite understand your question. So,
Yeah.
so for trees, we
No.
extend
I mean,
approach.
are there any kind of theoretical theorems or statements, no, saying trying to maybe evaluate what is the quality of a tree model given some properties of the data, no? So
Oh, I see.
or do we have to run the algorithm and then just to see how well it works?
I see. Yeah, so sorry, we don't currently we don't have such theoretical guarantee on it. Yeah, what we have is just some empirical experience, for
Okay.
tabular data, usually tree has a good performance, so you can try tree.
Mhm.
So currently we don't have such a theoretical guarantee.
Yeah. Okay. No, that's
Yeah,
also
so
good
sorry.
if it works. Okay. So is there are there more questions from the audience?
Yes, I have one more question to ask. So here, what was the what was the deciding factor of the communication round? Was it only one communication round made, or to
Yeah.
get it done?
So for the communication, here you can
Yes.
see that we do the batching. So after the queue is full, we send the histogram, some collection of histogram.
Okay, so there is only one round of communication that was made between the.
Usually in each level, we only have a single round of communication.
Okay.
Because in each level we do that parallelly, we aggregate a histogram, we group the histogram, we share the group the histogram.
Okay. Thank you.
Yeah, you're welcome.
Okay, there's a other question by Ricardo.
Yeah, so here differential privacy is an option. Sorry about it. So here in here we didn't present result differential privacy. So by default we do not apply differential privacy. Differential privacy is an option to apply. Here you can see when you compute a histogram, you can use differential privacy to add noise to the histogram and share the histogram. So before you share the histogram, you can use differential privacy to protect histogram. But of course, differential privacy will degrade the model performance. Yeah. We have some results of differential privacy, but I didn't show it here.
Okay, so
yeah, you're welcome.
Ricardo says thanks. Okay.
You're welcome.
Oh, man, that's good. Okay, is there maybe one more question? Does not seem to be the case. So then, yeah, that's fine. So I thank the speaker again. Thanks for being here. And
Thank you for having me.
thank you for your talk.